When we talked about sampling distributions in Chapter 9, we looked at a few problems where we might take a claim made by a company, such as they fill their cans of soda to 12 ounces. Then we would look at a set of data from a randomly selected group of cans of sodas and look at how likely it was to get an average of, say, 11.9 ounces if the company was actually attempting to fill them to 12 ounces. What we're going to move into in chapters 11 and 12 is a formal procedure for comparing some observed data with a hypothesis whose truth value we want to assess. So that hypothesis is going to be the claim that the company is filling the cans of soda to 12 ounces. Our observed data is coming from our simple random sample. We're going to create or construct a probability based on the sampling distribution and going to ask the question, how likely is it that this random event occurred if, again, the claim is accurate? So how likely is it that 50 cans of soda produced a mean of 11.9 ounces if it's actually true that the company is filling them to 12 ounces? So some of this might seem familiar. We're just going to put, as it says, a more formal process to this idea. Just as with confidence intervals, we had to get used to stating the population, the parameter, and the conditions. We're going to add another layer on when we do significance tests or hypothesis tests in Chapter 11 and 12. We are going to have some type of hunch about a phenomenon. So if we're talking about our soda can example, then we're thinking maybe that if our simple random sample produced an average of 11.9 ounces, our alternative hypothesis is going to be that we think the company is maybe underfilling the cans. We're going to test this against something called the null hypothesis. The null hypothesis is what we're suspicious about. We're going to try to find evidence against it. As it says here, this is usually no effect or no difference from the historical data or from the claim that maybe a company is trying to make. So the null hypothesis would be that the mean fluid ounces in the cans of soda is 12 ounces, and our alternative is that it's going to be less than that. We're going to practice putting our hypotheses in both symbols and words. This is going to help with an interpretation in the end, because again, just like confidence intervals, the big piece in the end is going to be taking our findings and putting them into a clear and concise statement. It can be difficult to start to come up with hypotheses when you first start looking at significance tests. I tend to create my alternative before anything else because usually we'll be posed a question, is there evidence that the company is underfilling the cans, or is there evidence that the mean is not as that has historically been true? Whenever you create your alternative and it's going to use a less than, greater than, or not equal to sign, then I go back and oftentimes do the null hypothesis, which will use the same symbol, the mean or the proportion, the same number, but it will just replace an equal sign in place of the less than, greater than, or not equal to that you created for your alternative hypothesis. This will make a little more sense when we look at some examples, and I hope that you've already read the chapter so that you've seen a little bit of what these hypotheses will look like. Another important piece is that both hypotheses are stated in terms of parameters, not statistics. So we're going to be using mu or p, not x bar and not p hat ever in our hypotheses. We want to be testing a claim about an entire population based on our sample data, but the sample data is not going to be used in the hypothesis statements. If you hadn't had a chance to read example 11.2 on page 688 of our textbooks, please pause the video and do so before moving on. The last line of this example that says, do these data provide good evidence that the response times have decreased since last year? That right there is telling us the alternative hypothesis that we want to test. So have the times decreased? We're going to take last year's response time, the 6.7 minutes. Again, we're going to put it in terms of mu, and to see if they've decreased, we'd use a less than sign. H sub A is used to denote that we have our alternative hypothesis. This right here is our hypothesis in symbols. I do have a unit on there, and you want to put that in whenever you have those available. Then I have our alternative hypothesis listed in words. The mean response time to call all accidents involving life-threatening injuries for this city is less than 6.7 minutes. And we want to be as specific as possible. So because the simple random sample is just coming from the entire city, we can only generalize our results to this city in particular. Then I go back oftentimes and state the null hypothesis because I think that one can be harder to come up with. The null hypothesis uses H sub 0 instead of H sub A, and it just takes the same parameter, so we're still talking about mu, the same number, 6.7 minutes, but puts an equal sign in between them. That's what in this example, that's what the average was last year, and we want to test to see whether or not we've decreased from last year. So that creates your null. Your null should always have an equal sign. And then to put this in words, the mean response time to all accidents involving life-threatening injuries for this city is 6.7 minutes. We can refer to our alternative hypotheses as being either one-sided or two-sided. A one-sided alternative is what we just looked at. We want, or we are interested in deviation in one direction from the null hypothesis. So our alternative in the last example was that the mean was less than 6.7 minutes. If you look at example 11.3, here shows you a two-sided alternative. This is where we're interested in any deviation from the null, but we might not have a suspicion as to whether the data are going to support a less than or a greater than. So in this case, we're going to look at an alternative hypothesis where the mean is not equal to something. And to use the value from example 11.3, they have 0 in terms of a test score. So if you haven't read that example, again, pause the video and do so. In practice, we want to state our alternative hypothesis before the data have been assessed. So usually we'll have some type of suspicion before we even look at a simple random sample or before we even take a random sample from our population of interest. You'll see that whether we use a one-sided or a two-sided alternative will make a big difference in our calculations, or I should say it could make a difference in our calculations. So we don't want to do the calculations first before we state the alternative because that can have an impact on the results of our study. You're used to checking conditions for a confidence interval, and the good news is that they will carry through to chapters 11 and 12. The same conditions will apply to hypothesis testing or significance tests. We can use those two interchangeably. They'll change slightly when we get to chapter 13 in terms of comparing two different populations, but for now, you should be pretty comfortable with these. So we have our simple random sample, and we're going to just read the problem to see whether or not it's been satisfied. If we're performing an experiment, we're going to look for some element of randomization if a true simple random sample couldn't have been taken from the population. When we're looking at means, you know we have several different ways to assess whether or not our normal calculations will be accurate. Central limit theorem, we might be told that the normal distribution occurs, or we might look at a box plot or a histogram in order to determine whether or not we have symmetry and we are free of outliers. I want to stress that you should draw any plot that you look at. Typically, you're going to want to use a box plot instead of a histogram. Some of you on your last quiz used a histogram and it may have looked a little funny because we only had, say, 10 data points. Because you're only going to be assessing the distribution graphically when the central limit theorem is not in place, so when we don't have a sample size that's 30 or more, a box plot is going to give you a better idea of the shape of the data. So I do recommend that you default to the box plot instead of the histogram and the modified box plot so that you can see if there are any outliers. Draw it. You want to say that the graph, or you want to see that the graph is approximately symmetric. Don't call it normal because a box plot can't tell you whether or not data is normal. Or your other option is to look at a normal probability plot, draw it. Hopefully it's fairly linear so we know our calculations will be accurate. For proportions, we don't have any of these processes that we look at for means. We will always use the NP and NQ rules to see that they're greater than or equal to 10. Again, the central limit theorem cannot apply to proportion problems. And lastly, for independence, when we're drawing without replacement, we want our population to be at least 10 times as large as the sample. A test statistic is basically going to be a standardized value. It'll be a kind of z-score or t-score depending on the distribution that we use in order to assess how far our sample data is from the parameter. We'll use our test statistic to look up what's called a p-value, which will be a probability, and a lot of these calculations are going to feel similar to what we've done in Chapter 2 and with the normal curve, but also we're going to bleed into the t-table that's in the back cover of your book to find the probabilities associated with a t-distribution. Standardizing the estimate or finding the z or t value is going to feel familiar. Starting to talk about means here, if we know sigma, then we'll be looking at a z distribution, just as we started talking about confidence intervals. We do know that it's not likely to come across this scenario because we don't likely know sigma without knowing mu. And so just as we had for confidence intervals, the only reason you would use a z distribution for a means problem is if sigma was given to you. In any case, if it does come up, this is how you're going to find your standardized estimate. You'll take your sample mean minus the suggested mean for the population, divide it by the adjusted standard deviation or the standard error from the sampling distribution. You would then take that z-score and use table A to look up the probability associated with it. The more likely case is that you do not know sigma and you're going to be using sample data in order to construct a standardized estimate. So this is when we use a t-value. Looks almost exactly the same, except that you have s coming from your sample instead of sigma. If you were to use the 1-var stats, you want to make sure you use s instead of sigma. Even though sigma shows up, that's not the correct value because that's assuming that all of the data you entered are the population of interest, and it won't be. It will be a sample. Once you get this t-value, then you'll use table C or B, and depending on whether you're looking in your book or you're looking at the handouts I gave you, just make sure you're reading the title of the table. You're using the same idea of degrees of freedom that we used from Chapter 10, and you'll look up the p-value accordingly. For proportions, we always use z-scores. We're not going to be given a sigma or an S value for proportions because we calculate them solely based on the proportion that we got from our sample. So proportions are a little bit different in that way, but it's the same concept from Chapter 10. So you'll go back to your z distribution and table A. Just to reiterate, it's not that you'll never come across these calculations, but it's much more likely that you'll use these two here. Computing a p-value will be the next step in the process. So you're going to state your population and parameter, state your hypotheses, check your conditions and show that you've done so, get a test statistic, as we did on the last slide, and then you'll look up a p-value, which is just a probability. This probability assumes the null hypothesis is true. You're going to know in which direction to shade underneath the curve based on the alternative hypothesis. So if it's less than, you'll shade below the curve. If it's greater than, you'll shade above. Not equal to is a different scenario, and I'll get to that in a future slide here. The smaller the p-value, the stronger the evidence is going to be against the null hypothesis. So let's think back to our soda can example. In that Chapter 9 test, we had a claim from the company that the mean fluid ounces in each can of soda, or in the cans in general, were 12 ounces. We took a simple random sample of 50 cans, found that the result was 11.9 ounces. We calculated a probability of that happening. That probability was, I think, around 3%. And so what that 3% means is that if it's actually true that the company is filling the cans to the stated 12 ounces, getting a simple random sample of 11.9 ounces, there's only about a 3% chance of that occurring. Because that probability is so small, and because it happened, we're suspicious and we should think that the company might be underfilling their cans, since there's such an unlikely chance that a simple random sample would produce 11.9 ounces opposed to the 12. You're used to using the Z-score table, table A, to look up p-values already, probabilities. The t-value table is going to be a little bit different. You won't be able to come up with a probability exactly, but rather than a range, and we'll look at some examples of that. Let's look at how to find a p-value in a few different scenarios because it's based on the alternative hypothesis. Because this is a means problem, and I can tell because it's using mu in the alternative hypotheses, and because the test statistic is a z-score, I know that this must have come from a problem where I knew what sigma was, so I was using that first of the 3 calculations that was shown on the other slide. I'm going to draw a normal curve. I'm going to put 0 right in the middle. We know that 1.7, because it's positive, would fall above 0. And this first alternative tells us to shade above the curve because the alternative hypothesis is greater than 0. I'm going to look up 1.7 in table A. I will see that it gives me 0.9554. And because I want the area above, not below, I need to subtract that from 1. The p-value in this case is 0.446, and I'll show you what to do with that p-value momentarily. For the next scenario, we have the same test statistic, 1.7. It will fall above 0. But in this case, our alternative hypothesis is less than, so we actually want to shade the area below. And that p-value then will be the exact value that popped up on table A. And so this is a rather large p-value. You'll see that this is not strong evidence against our null hypothesis. But I don't always have to subtract. That's the point I want to make from here. Lastly, the not equal to case might feel a little different. We'll still start by drawing a curve. We'll put 0 in the middle, but what not equal to is going to do is look at 1.7 and negative 1.7, and it will look at the 2 tail areas corresponding to those z-score values. We found what one of those tail areas was in our first example at the top of this page. So to find what both of them are combined, we just need to double that 0.0446 result. And so for this scenario, we'll get a p-value of 0.0892. To reiterate, our p-value tells us how rare an event is, and the rarer the event, the more likely it is that we're going to be suspicious about our null hypothesis. We need to have some type of benchmark, and sometimes the problem's going to give you this benchmark. Sometimes you're going to have to use your best judgment, and you're going to default to 5% if you're not told. The most commonly used significance levels, and that's what we're going to call it, a significance level is kind of our benchmark, is 5% or 1%. Sometimes you'll see 10%, and that's going to show that something is too rare to occur by chance. We think that something is wrong with the null hypothesis. If a probability is less than or equal to the 5% or 1%, 10%, whatever we're using, we say that the data are statistically significant at that level. That's oftentimes called an alpha level. So you're going to see this alpha symbol used, and you'll see the book refer to an alpha level or a significance level. Let's say you were given a p-value of 0.03, or you calculated a p-value of 0.03. This would be significant at an alpha level of 5% because it's less than 5%. And in that case, we would reject the null hypothesis, meaning we think there's something wrong with that claim. It would not be significant at the 1% alpha level because the p-value has to be smaller than the alpha level in order for us to think it's too rare of an event. So here we would not reject the null hypothesis and say we don't have enough evidence to show or to support the claim that the null is not true. So your p-value is going to tell you what to do with the null hypothesis. That's going to be the first statement in your interpretation. You're either going to reject the null hypothesis or you're not going to reject the null hypothesis. You do not accept a null hypothesis ever. You're just going to either not reject or reject it. If you reject it, your p-value was smaller than your alpha level, and you think there's convincing evidence that the null hypothesis is not true. If you do not reject it, then your p-value is greater than your alpha level, and you don't think there's enough evidence to show that the null hypothesis isn't true. If you think about a court of law, I don't know if any of you watch law shows like I do, but when the jury gives their verdict, they don't ever say that the person on trial is innocent. They say they're guilty or they're not guilty. Not guilty doesn't mean they think the person didn't do it. It's just that they don't have enough evidence to say that they did. And this is an important distinction in the law as well as in statistics. These next couple slides just reiterate a little bit of what I have already stated, so I'll just let you read through them. Let's go back to the calculations we did earlier just to wrap this up. We had a test statistic of 1.7. We have in our first scenario an alternative hypothesis that our mean is in the greater than direction. We found our p-value using table A, looking at the appropriate shaded area under a curve. The question here is, are any of these statistically significant at alpha equal to 5%? Because this first value, 0.0446, is less than 5%, this is a case where we would reject the null. And so yes, it is statistically significant at the 5% alpha level. In neither one of the other two is the p-value less than 5%, especially in this next one. We have a very large p-value, which would tell us that the occurrence of our simple random sample is a very likely scenario given that the null is true. So in this case, we do not reject the null. The data are not statistically significant. And the next one, lastly, the not equal to scenario, this is just a little bit too high, so we would also not reject the null in this case. Keep in mind that the 5% is a little arbitrary, and if we used a different alpha level, like 10%, all of a sudden this last example would give us a scenario that we do think is statistically significant, and we would reject our null hypothesis. We would say that we think the company is making a claim that is inaccurate, which can have some pretty serious consequences. So understand that the alpha level is a bit arbitrary. There are benchmarks for different scenarios, and the alpha level is chosen based on the severity of the consequences of either rejecting or not rejecting. More of that will come as we unfold some different examples throughout this unit. Because that significance level can have an impact on whether or not we reject or do not reject the null hypothesis, we need to make sure that a significance level or an alpha level is established before we find a p-value. So don't choose one after the p-value is found. You wouldn't want to look at that last scenario on the last slide, see that roughly 8% and say, okay, I'm going to choose an alpha level of 10% so that I can reject it. Or I'm going to choose an alpha level of 5% so that it's not rejectable. You don't want to do that. So make sure you have a clear idea of where you're going before you do any calculations, just as you would in stating the alternative. It might take some practice to get used to looking up a p-value for the t-distribution. Let's suppose you run a test for means with an unknown population standard deviation. We know from confidence intervals that this is the most likely scenario for means, and it's going to require using this different table. So you're going to find your test statistic, and in this scenario, we got a test statistic of 1.81. We used a sample size of, say, 20, and so we have 19 degrees of freedom. I need you to look at your t-distribution table. So table C if you're using the cover of your book, and it should be in the back, or table B if you're going to use the tables that I passed out to you at the beginning of the year. I want you to go to the 19 degrees of freedom row, and you're going to start dragging your finger across until you find where 1.81 would fall. You're not likely going to find that value exactly. So as I walk across, once I get to, I think it's the fifth value over, I have 1.729. The next value is 2.093. Our test statistic of 1.81 would fall in between those two values. Once you find the two values in which your test statistic falls between, I want you to go and walk up to the top row, very top row that says upper tail probability, and you're going to find then the two tail probabilities that are associated with those two t-values. So in this case, it's 2.5% and 5%. That p-value then is somewhere in between 2.5% and 5%. We don't have to know exactly where it is if it's between those two values. If we're using our common alpha level of 5% and it's a one-sided test, then we know that our data are going to be statistically significant. It really doesn't matter if it's 3% or 4% or 3.5% because all of those are going to be less than your alpha level. If it were a two-sided test, we would double those values because we'd want to be looking at the upper tail and the lower tail. So our 2.5% to 5% would become 5 to 10%. And then in that scenario, if we were using the same alpha level of 5%, we would not be able to reject our null hypothesis. The data would not be statistically significant. Because the table shows symmetry, and you'll notice on this t-distribution table that there aren't any negatives expressed. If you had a t-value of negative 1.81, you'd use the same process, and that really shouldn't matter in this case. So when running these tests by hand, you're not going to find a p-value exactly. You're literally going to state, and you'll see that I did this on some of your examples, you're literally just going to state that the p-value falls between this and this. That range should be sufficient to draw your conclusion and make your interpretation. Your calculator, on the other hand, can do this more precisely, and we'll talk through that before we wrap up this PowerPoint. I want you to be able to do these calculations by hand, but just as you had the option with the confidence interval to use your calculator to check your work or to find a more exact p-value, or if it's a multiple choice problem, certainly the calculator can save you some time. You're going to find the hypothesis tests or the significance tests in the same spot you found the confidence intervals. So you'll go to your stat button, scroll over to tests. You should see that the first test available is a z-test. This is going to be for means when sigma is known. So why don't you get out your calculators, check out that first function. When you look in the z-test, just as you had the option for confidence intervals, you can either input the data because you have the data organized in a table, or you can put in the stats because you're just given the X bar and the standard deviation, the sample size, etc. When it asks for mu sub 0 in either case, that's the number that you're using in your hypotheses. So if we were using the paramedics example, it would be 6.7. If we were using some of the other examples we looked at, they might be 0. It all depends on what your hypotheses state. Then it also gives you an option to choose which alternative hypothesis you're looking at, and then you can calculate it. The only difference between functions 1 and 2, the z-test and the t-test, are that the t-test is more likely the case because you're going to use s instead of sigma. So you're going to be using function 2 more often. And then lastly, once we get to proportion problems, function 5, a one-prop z-test, there's only one choice for proportions, so you'll be using that one should you have a proportion problem that you're looking at. And that will come in the next couple days.